Welcome to the next lecture in the course Basics of Mechanical Engineering 1. We have discussed majorly about the mechanics, about units and dimension in the previous weeks. About the solid mechanics majorly we have discussed in the past weeks, and now we have started introducing the machines, theory of machines. Regarding the laboratory demonstrations in the solid mechanics, you learnt about the tension, compression, different properties, and how do we test them. A brief introduction was given. This lecture and this week would be covering a detailed laboratory demonstrations on different experiments that we conduct to have the testing of the material at different levels. This lecture basically be covering testing for tension and compression. That is, we will try to have a tensile test and compression test in this lecture. First, we will have a quick introduction that what is material testing and why do we really need it. Then we will discuss about the tension test and compression test. In those, we will try to recall the theory that we have discussed in the previous lectures. We will try to go through the procedure. We will cast a glance over the demonstration, that is the video demonstration on YouTube, and also simulation that is developed by the VLab, that is virtual lab setup, initiated or mentored by IIT Madras, and this setup for testing is developed by different institutions in India. The demonstrations which I will take for these two tests, tension and compression, are developed by NIT Suratkal. What is material testing? The question what is material testing could be answered in this way. Material testing is a critical aspect of engineering that involves evaluating the properties and performance of materials under various conditions, that is properties of the materials and performance of the materials, both the characteristics we try to understand, and this helps us, or the engineers are helped with understanding how materials will behave when subject to different loads. So, which is essential? This is an essential requirement for designing safe and reliable structures and components. Safe, reliable, I would say, machines, components, and we will talk about the compression test that is majorly having application in construction. That is, I would like to put here is safe structures. Now, overview of material testing in engineering. Material testing encompasses a range of techniques and tests to assess the various properties of materials. These tests can be broadly categorized into these categories. It is mechanical testing, in which we have tensile test, which measures the material strength and ductility by pulling it apart until it breaks. This is the tensile test we will go through in this lecture. Also, compression test is there, which assesses the material's behavior under compressive forces. That is, we try to apply the forces in the opposite directions, but towards the material, that is compression test. Then we have hardness test, which determines the resistance of the material to deformation. Impact test evaluates the material's toughness and ability to absorb energy during a collision. So, we have talked about the test, very brief introduction was given. These are the two setups which are given. This is a bending setup. We will talk about the bending setup also in the coming lectures. So, why testing is important? The importance of understanding material behavior under different loads, first and the foremost thing is safety. Prevents accidents by ensuring materials can withstand operational stresses, that is factor of safety that you have learned. We always design based upon the actual application, factor of safety is fixed, and factor of safety, because if factor of safety is always optimized in a way so that material consumption is also not there very heavy, and also the strength is also obtained. If factor of safety, suppose we just put 10 factor of safety all the time, the material strength or the size of the material that we need to take would be 10 times higher, weight would be 10 times higher. So this is a very critical factor to understand or to put the factor of safety when weight or material usage is also very important factor. Then comes reliability. Predicts material lifespan for timely maintenance and replacements. Material lifespan we are talking about, that is why reliability is major concern here. Optimization selects the best materials balancing performance, cost and weight. These are the parameters I just mentioned: performance, the cost, it is the amount of material that we use, and the weight of the material. Factor of safety is also factor here. Regulatory compliance meets industry standards and regulatory requirements. We will see the specimens which are there for different testing are always based upon a standard. The ASTM standard is there, other standards are there. So we will see the regulatory compliance are always important when we try to develop any product and the test is conducted to understand the material properties. Then innovation develops new materials and improves products through material insights. New and modern material are coming up, where we are having nowadays for functionally graded materials, we are having composite materials, different tests are conducted over them, so that we get the strength as and when required. The different materials are developed and tested, and those are always the graphs or the test output that we receive or we develop is equivalent to what is there for the regular test that we do for milestone, for cast, and that is for majorly ductile material. For brittle material, different tests are conducted and different parameters which are to be calculated, maybe tensile strength, compressive strength, hardness, impact strength, all those are taken based upon the actual application. So what is a tension testing or tensile testing? Tension testing is a method of determining the behavior of material under axial tensile loading. So material is under a load, we are pulling apart the material in two different directions. So this is a specific setup. We will show you the setup in a demonstration here, and this is what is the typical shape of a specimen that is under testing. It involves a tensile force to a specimen and measuring the response. So this includes materials deformation and fracture, which the eventual event is fracture. I will put it here, this is for deformation and eventual fracture. Key properties obtained from a tension test include the ultimate tensile strength, yield strength and elongation at break. Now, what is the importance of tensile testing? Why is tension testing important? It ensures materials can withstand tensile forces in real world applications. It helps in determining the material's load bearing capacity and ductility. Ductility and brittleness was discussed in one of the lectures in the last week by Professor Ramkumar. So those tests we will see how do we conduct in a laboratory environment. Critical for quality control, material selection, engineering design, and so it provides data for failure analysis and improvement of material properties. So that is stress strain diagram is developed. This is a stress strain diagram for a ductile material. Typically, if you say this is for mild steel. Next comes the procedure. First and the foremost point, the first step here is preparation of the specimen. So this is a typical specimen. The specimen is elongated here. The forces are in both the directions here, and it is getting elongated. Standardized dimensions. The specimen is machined to standardized dimensions as per ASTM, ISO or other relevant standards. Common shape include a cylindrical dog bone or flat specimens. This is a dog bone specimen that you can see in the figure. It is a round specimen. Surface finish, the specimen's surface is finished to avoid any stress concentrations like scratches or notches which can affect the result. But there is a video here as well that I will show you the laboratory demonstration, and I will also walk you through the simulation in the virtual laboratory setup. So, let us first go through the procedure steps. Second step is mounting the specimen, that is grips. The ends of the specimen are securely gripped in the testing machine. That is, when the specimen is there, these are the ends of the specimen, these are mounted here in the machine. So, the grips include, it could be hydraulic, it could be pneumatic, or it could be even mechanical wedges. Purpose is uniform load distribution. So, that is how the grips are designed, and different materials are there for which the sizes of specimen could be different. Next is alignment of the specimen. Ensuring proper alignment of the specimen with the load axis is crucial to avoid bending stresses. I will show you the virtual laboratory experiment simulation for mild steel and cast iron after the procedure. Next step is application of load. Constant rate, tensile load is applied at a constant rate, typically controlled by the cross head speed of the testing machine. Slowly, there is a nut and bolt mechanism. The machine is applying load slowly. It is a gradual load application, and there is a gradual elongation of the specimen, and the graph is also plotted accordingly. We get the data. How do we plot the graph? We will see. The rate is specified by the testing standard. Data recording. The machine records the applied force and corresponding elongation of the specimen continuously. This recording is either downloaded or it is noted using pen and paper. There are modern machines where you just get the complete information using the DRO, that is digital display that is there, and you can try to get the whole information in the machine itself. But there are standard machines which do only mechanical testing, and other calculations could be done either manually or using your MS Excel or other softwares. So there is a specified testing standard. Again, I am stressing here, this is a specific standard or testing standard which ensures consistency. So consistency is one factor, then comparability is also one factor. Comparability of results. That is one test we conduct at IIT Kanpur, another test for the same specimen we conduct at MIT US. Then the comparability of the results would be there, the results would be similar provided the material has come with the same specifications. Then comes the data collection, that is we obtain the stress strain curve here. The recorded data is used to plot a stress strain curve. Stress is calculated as force divided by original cross section area, and strain is the change in length divided by the original length. Elastic and plastic deformation, the curve shows the elastic region, that is the linear part where the material deforms but returns to original shape when the load is removed, and the plastic region non-linear where permanent deformation occurs. This we have seen multiple times. This is elastic area, then we go to the plastic region, and then we reach our ultimate tensile strength, and then we go towards the fracture limit. It has been given the points: A is proportional limit, B is elastic limit, C is ultimate strength, and D is fracture limit. Then we try to conduct the fracture and analysis, that is ultimate tensile stress. The maximum stress the material can withstand is defined as the highest point on the stress strain curve. So this is ultimate tensile strength, it is shown here. Yield strength is the point where permanent deformation starts, often determined using 0.2% offset method. So here is the yield strength, you can see here 0.2% offset method, the point where the permanent deformation starts. Then elongation at break and reduction in area. These values are measured to assess the ductility of the material, that is what is the total elongation that has happened for a specific material. More ductile material would be having higher elongation, less ductile material will be having lower elongation, brittle material would have almost zero elongation at all. So this is, you see, this is ultimate tensile strength, and this is where the fracture limit is there, and we try to understand the system. So here I have a video that is developed by Center for System Design at NITK Surathkal, and this is a video that I will demonstrate here. I will come to the full screen mode and try to play the video where the complete demonstration is there. So this is tensile test for mild steel. This is our experimental setup. This is a universal testing machine that you could see here. The object is to study the mechanical properties of mild steel under tension load. So this is a mild steel specimen. You can see the specimen as per the ASTM standards. First we measure the initial diameter. In two perpendicular directions we measure it, and we get the initial dimensions here like 12.34 millimeter, 12.33 millimeter. Then we mark a line straight over it using the chalk, and we locate the center point here. Using the scale we are marking the center here, and either side we are marking the pointers here. Punch marks are made at the extreme points, and these punch marks are made at the distance of 2.5 times the diameter of the specimen. It is 2.5 D. I will show you in the simulation as well. You see the punch marks are being made here, and these punch marks are made one by one, and then the test specimen is fixed in the cross heads, and adjacent cross heads are moved now. Now we are locking the specimen here. The extensometer is then mounted so that we also measure the elongation, and these marks will show you the elongation is there. Now the machine is also set at 0.0. So now the machine is started for gradual application of load. You see, gradually the load will be applied, and extensometer is showing that slowly elongation is also happening. So we keep on noting the extensometer readings at regular intervals. Manual recording is there, that is pen and paper recording is there. You can see the elongation is there. Then we remove the extensometer. The ivory scale is also showing the reading here. You can see the specimen is broken here, and this is cup and cone shape breakage. Now we measure the distance here, that is the elongation from the points which were marked. Also the diameter is measured using the vernier caliper, and we plot this load versus ivory scale reading graph, and also load versus extensometer reading. Both the graphs are plotted, and then we use calculations or do certain calculations using the observations to measure the Young's modulus, over the yield strength, and other properties which are there, or other measurements which are required. I will take you to the virtual laboratory simulation. There you will see how this is all conducted. So let me try to first talk about the equipment for tensile testing. So this is a universal testing machine in which we have load frame, that is main structure that supports the specimen and the loading mechanism. So this is the main structure. We have a load frame here, and we have crosshead, that is movable crosshead, that is here. The crosshead is a component that applies tensile load to the specimen. Now load cell is here, a device that measures the force applied to the specimen with high accuracy. There is a load cell that measures the force that is applied. Then extensometer is there. Extensometer is an instrument that measures the elongation of the specimen. Elongation of specimen is measured using extensometer. This is typical universal testing machine. Let me also show you different grips. These are different grips that I just mentioned in the previous slides. You can see a mechanical wedge grip. Use mechanical wedges to clamp the specimen. There are mechanical wedge grips using just a mechanical force itself they try to grip. And then we have hydraulic grips that use a hydraulic pressure to clamp the specimen, providing uniform gripping force. So these are hydraulic grips which are here. Pneumatic grips are there that use air pressure to clamp the specimen, useful, and these are useful for software materials. And there are computer software available. The computer software in modern universal testing machines are equipped with the software that records and processes this test data, generating stress strain curves and calculating key mechanical properties automatically. So, this is a software interface of a modern machine in which you can say the data is there, tensile load, what is the load applied to 188 kilonewton, and we have different parameters. We have the stress strain curve already plotted here. We have the tensile display and time curve, that is how the time is flowing when we testing is going on. So, temperature control is also optional nowadays, because to simulate or to work for the real time situations when the machines or the systems are there under a tensile load at a specific temperature. For example, in aircraft itself, in the components, when in the engine, those are heated, those are also under tensile load at certain stages. So, that temperature control systems are also there, that is environmental chamber is there, which is used for testing material at different temperatures, simulating the real world conditions. Then safety enclosures are there, that is protective shields ensure the safety of the operator by containing fragments if specimen fractures violently. So, this you can see, this is a glass door that becomes our protective shield. So, there could be certain applications, as I mentioned about the aircraft applications. So, equipment calibration is very important here. First point here is accuracy, another point is compliance. Accuracy means regular calibration of the load cell, extensometer and other measuring devices is essential for accurate and reliable results. So, this is a regular calibration that is required for having the reliable results. On the other hand, there is also compliance. When we are trying to submit our results to the industry or the people who are coming to us for testing, there are industry standards. So, to ensure compliance with industry standards and specifications, maintaining the validity of test results is important. So, that is why equipment calibration is also important. Now comes the application. You can see in aircraft different materials are there. 10% of that is steel, 15% is titanium. Titanium, you know, is having high strength to weight ratio. With a very low weight, strength is very high, because weight is a major consideration when we are trying to design an aircraft. So, titanium is there, aluminum is there, and advanced composites are there nowadays. 50% of the material is advanced components, 5% of the materials are also there. So, in aerospace industry, tension testing is critical for assessing the mechanical properties of materials like titanium alloys used in aircraft structures. These tests ensure that materials can withstand the extreme loads and stresses which are encountered during flight. This contributes to the safety and reliability of the aircraft. So, let me now come to the laboratory simulation, that is virtual laboratory simulation, and I will try to show you the experiments under the virtual laboratory that is developed. This is mild steel test virtual laboratory. You see, in this we have a complete record of the test. For example, what is the aim of the test? To study the mechanical properties of mild steel. So, study mechanical properties of mild steel specimen under tension load. Then we have a complete theory, the theory that we have discussed through this course as well, that what is elastic deformation, what is the flow region, material handling, material hardening, necking, and what are the formulas, elongation, change in length per unit original length that is there. Then we have reduction in area, change in area per unit original area, tensile strength is ultimate load per unit area, then yield strength is yield load per unit area. We are talking about original area only. Then we have modulus of elasticity, that is slope into gauge length per unit area. So, all these relationships are given here, and how the fracture happens. Slowly it is elongation, it is necking is there. Then you say small pores are there which are there, and the fracture starts. The crack grows at 90 degree to the applied stress. So the maximum shear stress is here at 45 degrees, and then cup and cone shape is formed and fibrous and shear materials is obtained here. This is the theory of the test. This is gauge length. Gauge length is the constant length between two ends. So let me come to the next point. This was theory in virtual laboratory. The procedure that I am mentioning, the complete procedure is here. I will walk you through the simulation. Then we have some self-evaluation questions here as well. I will come to the questions. These are the questions. So that is pre-test questions. Before even conducting the test, you should be aware of that which law influence the material up to yield point. It is Hooke's law, right? Then while conducting the experiment, the mode of fracture observed in mild steel specimen is, what is the mode? It is cup and cone. Then what is the distance between punch marks in the experiment? It is 2.5 d. Yield point is the point on the stress graph where there are four options: failure of material occurs, elastic deformation commences, plastic deformation commences. Yes, plastic deformation starts at yield point. So it is plastic deformation commences at yield point. Elastic deformation of the material associated with toughness, ductility, hardness, permanent deformation. Because we are talking about elastic deformation, it is associated with ductility. Then we have the arrange in order the sequence of the experiment. When does ultimate load, upper yield point, elastic region, breaking load, lower yield, when it comes. So you know, in the order of having different loads or regions here, first there is a elastic region, that is a constant load and elastic deformation only, that is not at all permanent. So then we get the upper yield point for where it falls to the lower yield point, and when we keep applying the load, we reach the ultimate tensile strength, that is the highest point, and then only comes the fracture or the breaking strength. So here, which is the option? Upper yield point first, it is first option A could be there. Lower yield point, elastic region, no, the first is elastic region. C or D could be the points. Elastic region, lower yield point, no, first is elastic region, upper yield point. Yes, this D is the option. So let me try to submit the quiz. Yes, I have gotten 6 out of 6. That is all the answers are correct. So you should definitely go through these virtual laboratory experiments, and this is the pre-test questions which are there. Now we come to the simulation. In the simulation, you see it has been shown that this is the objective to study the mechanical properties of mild steel specimen under tensile load. Apparatus used is universal testing machine, dial indicators, accentometer, scale and vernier caliper, and we go to the next step. Previous was the step 0 when we just showed you the machine. Step 1 is measure the initial diameter of the tension test sample into perpendicular directions using vernier caliper. So we have to, it is showing an arrow mark here, that is when we click at this point, the vernier caliper will start measuring this diameter, and this diameter it measured is 12.82 millimeters. Now it is from one direction, from other direction, from the perpendicular direction. For instance, if this is my specimen, I will measure the diameter from this side, and then I will measure from this side 90 degree. This is one direction and other direction. From both the directions, diameter is measured. This also ensures that the diameter is constant, it is not elliptical. So then I again click here, it is measuring the diameter from the second direction as well. The diameter is 12.82 as well. So the average diameter is 12.82, which is my initial diameter of the specimen. Let me go to the next step. Step 2, measure the length of the specimen between the grips using a scale. So I have to now click on the scale, it will measure the length. Yes, this length is known as between grips length or gauge length. So this length is 192 millimeters. Then is the next step. Now once we mark the center lines using chalk, that we showed you in that video demonstration, punch marks are made at 2.5 D, 2.5 times of the D. So here I will click on the hammer, first punch mark, then second punch mark. You can see here 2.5 D is 2.5 into 12.82 is equal to 32.05 millimeters. Then I keep on marking the punch marks here, third, fourth. When I click only, then it works, fifth. That's all. So this specimen is now ready to be mounted over the machine. So now here there is a wheel, the crosshead, I will click the wheel and wheel will be rotated to open the distance between the crossheads. Now drag the specimen, there was a text popped up here, drag the specimen to this place. I will drag the specimen here. Now again I will rotate the wheel to close the distance so that the specimen is held between the lens. Then extensometer is held here or mounted here. You can see extensometer with 2 dial gauges which is mounted here. Let us go to the next step. Step 5 is readings on the dials A and B of extensometer are adjusted to 0. So we adjust the reading to 0 here. And second reading is also adjusting to 0. You can see it is something negative reading here. This pin, this needle in the dial gauge is at some negative value. When I click, it comes to 0. So least count of the extensometer is 0.01 millimeters. Let us go to the next step. Step 6 is now switching on the machine so that the gradual load is there applied. Green button is to be pushed here and the load is being applied here. Slowly you can see the extensometer is taking readings and the load is applied very gradually here. Slowly the reading is being added time and again. So this is now ready. So all the readings, that is load in kilonewton from 2.5 to maximum load that you could see here is 60 kilonewtons somewhere here, and ivory scale reading that is in millimeter is 56. It started from 1 millimeter to 56 millimeters. So we can download the data as well. If I click the download data, you can see it is downloaded here, and this is an Excel sheet that is obtained where the data is downloaded. This is just downloaded data, and we can use this to calculate our all the readings. So let me go to the next step now. Stop the machine. Red button is stopping the machine. 6th step is over now. The machine is stopped. Let me go to next step where it has now plotted the data. You can see at any point I can see the data that is there. Here you can see the data, the load in kilonewton, the extensometer reading for extensometer A and B. Both of them record the reading and the average value is taken. So it is given here. Ivory scale reading is also there. Based upon these reading only, you can see corresponding to value 50 of the load, 14 millimeter is the extension. So here you can see 14 and 50, the same reading is here. So this plot is gotten here. Now let me move to the next step where load versus extensometer reading is there. Let me see the data again. At around extensometer reading of 9.5, the load is 20 kilonewtons here. Let me see that in the graph. So at around 9.5 it is 20. So that means this plot is also obtained from the same observation table. So we can also view the slope, that is delta x, delta y is gotten, delta x is 4.3, delta y is 9.5, slope is 2.21. So we can keep getting these values, and this is how the specimen shape is there, that is cup and cone shape is there. And now we need to measure the diameter, that is the final diameter. Final diameter is 8.83 millimeters, and we also need to measure the distance between two notch points, that is the extension is to be measured. So we measure this distance. So length between the punch mark is 87 millimeters. So based upon these values and observations that we have gotten, initial diameter is this, length of the specimen between grips was this, punch mark at the interval of 2.5 d in millimeter is this. So this is what you have gotten distance. Final length between 3 punch mark in millimeter is 87. Final diameter in millimeter is 8.83. Original cross sectional area, that is A0 in millimeter square, is 124.68. Final cross section area at the neck point is 61.21 millimeter square. Least count in millimeter is 0.01. Gauge length of the extensometer in millimeter is 120. So based upon these we can do calculations of the yield strength, tensile strength, modulus of elasticity, percentage elongation, percentage reduction of area, and we can check the observation, we can check the graph, and once we put the values here, we can check the values as well. So this was this tensile test. I showed you the video demonstration. I showed you the simulation in the virtual environment using the VLab that is developed by NLTK Surathkal. I will also like to show you the tensile test for the cast iron. The procedure is all same. The next link is tensile test for the cast iron. Here only there is a change in material, rest all things are almost same, evaluation questions are almost same. Yeah, some questions could be different, but you can go through them. I will just show you the simulation and show you the final results. In the cast iron, we go through the experiments in the similar fashion. I click and find the diameter, then I again click and find the diameter in the perpendicular direction, then I measure the length, and we keep marking the punch marks at a distance of 2.5 D. Whenever it show arrow, I click, and then only it works. It is opening. I will drag the specimen. This is the cast iron specimen. I will then close it. Here dial gauge is used. So this dial gauge is set to 0 value. Then we switch on the machine. You can see slowly the readings are being generated when the gradual load is applied. And here the graph would be different. That only I wish to show you here. So these are the readings which are being obtained here. It is still going on. So finally it has broken. Yes, it has broken here, and we switch off the machine. Then we get the curve like this. We do not have any bumps like those were there in the ductile material test. So then I go to try to see the specimen. So this is a straight shape. So then I measure the diameter to understand the changes, to understand that the change is negligible, and we try to see the graph and observations and try to check that. So here you can see in the theory the specimen breakage is something like this. This is the proof stress, stress versus strain curve, yield point comes here and here it breaks. So this is how the specimen breaks. So this is a failure pattern of a cast iron, that is a brittle material. So brittleness and ductility, both tests are conducted. So next I will take you to the compression test in the next part of this lecture, where we will be conducting a test when the forces are applied in the opposite directions but towards the specimen. And we will also try to see how do we conduct that in a virtual laboratory, and we will try to understand the compression test in the next part of the lecture. Thank you.